In this example, you're asked to give the expected major product or products of each of the following reactions. Write no reaction if no reaction will take place. So in the future, when we get into more reactions, you're going to be evaluating these, and you're not necessarily going to know if it's SN2 or some other type of reaction. Because of where we are right now in the book, these are pretty much going to be SN2 reactions or no reactions. So in this example here, what we want to do is we want to go through the process of evaluating everything for an SN2 reaction. Do we have a good leaving group? Do we have a nucleophile? What is the solvent? What is the sterics of the substrate? Where is the substrate? So we want to kind of evaluate those things. As I've said before, I like to find the leaving group first, because if I find the leaving group and it's there, that means I can continue looking for the other components. If there's no leaving group, there's no reaction occurring, so I just stop there. So when I look at this, I'm looking for a good leaving group. We know that's things like halogens or anything that has negative charge being stabilized. So in this example here, yeah, we have a halogen here, but it's not attached to any carbon chain or anything. Okay, it's just a chloride. Most likely that's going to be our nucleophile, and that is going to exist as something like, again, I'm just going to write this in here. I'm just picking a random cation. That's going to be something like NaCl. Okay, it's just that sodium or whatever the cation is, it's often omitted. Please get comfortable with that. All right, so chloride, it's probably our nucleophile in this case. The acetone written below that, that is the solvent that this reaction is taking place in. And as you recall, acetone is an aprotic solvent, good for SN2 reactions. Now, this other species in here, this must be the substrate. It has the carbon chain, so it must have the electrophilic carbon. Question is, do we have a good leaving group or not? Well, we know it's not going to be any of the carbons. Carbon is not a good leaving group. What about this thing? Is that a good leaving group? Well, we have to think about that. And the way it's drawn might be a little confusing to you. So we have to, let me redraw this. We have to remember that that central carbon is bonded to an oxygen. That oxygen is bonded to a sulfur. That sulfur is double bonded to two oxygens. And then there's a methyl group here. So it is this whole component that I'm circling in red that is going to act as the leaving group. And why is that a good leaving group? Well, when it leaves, it's going to leave as this entity. And that negative charge is on oxygen, but it's not stuck on that one oxygen. It can move around. And that's resonance. And that is stabilizing. So that negative charge is being stabilized via resonance. And not only can it move to that oxygen, it could also move to the other oxygen. I'll draw this in just to illustrate where that charge is moving around. So that is a resonance stabilized leaving group, which means it's going to be a great leaving group, which means it's going to leave very easily. All right, I'm going to erase that. All right, so we've identified our leaving group, our substrate, our nucleophile. Well, what is that nucleophile going to do? It's going to attack an electrophilic carbon atom. I'm dotting the electrophilic carbon atom in red there because that oxygen is pulling electron density away from it. That leaving group is going to leave once that nucleophile comes in and attacks. So here's our chloride. It has all of these lone pairs. I'll draw them in. They're going to attack that carbon there. That's going to cause this thing to leave. And that is where we get the chlorine now bonded to that 3-carbon chain. And you could draw the leaving group in if you want. It's not usually what's important here, but it's still there. And that would be, this here would be the major product of this reaction. That is what you want to show.